Hello everybody, I'm going to be talking to you about solar eclipses that are coming to South Texas in the next few years. Now most people know that eclipses happen when the moon and the sun and the earth all line up. And so to understand that, we need to understand the motion of the moon. So here I've got a calendar for the whole of 2020 that shows you the phase of the moon. So if we look at each month, we go through different phases till we get to full moon, and then we get smaller and smaller until we get to new moon when we can't see the moon at all. And this basically happens once a month. We have a full moon once a month, we have a new moon once a month. But why does this happen? For the record, today we should be looking at more or less a very skinny waning crescent. The moon is on the way to getting to new moon, so the moon is getting smaller, and right now it should be a crescent. Okay, so why does this happen? Here I've got an image of the Earth with the moon going around it, and then somewhere way off to the right we have the sun. And the sunlight's coming in and it's hitting the moon, and it's always going to light up one half of the moon. But when the moon is in this position here, in the direction towards the sun, the lit up side is pointing away from the Earth, so we don't see the moon, and that's what we call new moon. As the moon moves in its orbit around the Earth, after a day, we're going to see a little bit of that lit up side. So a few days after new moon, we're going to get to see a waxing crescent, that is the crescent that's getting bigger. We can see just this portion of it. But the moon's going to keep moving, and as it keeps moving, we're going to get to see half of the moon that's lit up. Keeps on moving, so we see more and more of the lit up side until it gets to the other side of the Earth from the sun, and now we can see the whole of the lit up side. But it's going to keep moving, so as it moves along, it's going to get smaller and smaller and smaller until it gets back to the new phase. Now, one of the things that's confusing about this is we tend to think in two dimensions. So when we look at this, we look at the new moon phase, and it's between us and the sun, and this happens every month. So why don't we see an eclipse every month? Just to show you that more graphically, now we've got the sun all the way off to the left, and here you can see the Earth. The red line shows you the direction to the sun, so the shadow is directly in line with it. And here we have the moon, and it's going in its orbit around the sun, and the shadow of the moon does not hit the Earth because it's too high up. And so what we have is most of the time the moon is either too high up or too low down, so we're not actually getting to see a solar eclipse. Likewise, with the moon, most of the time the Earth's shadow does not line up with the moon, so we don't get a lunar eclipse every full moon. And that's why we can see the full moon. The sunlight comes in and hits it, and then bounces back to us, and we see the whole of that full lit up side. But occasionally they do actually line up, and so what you get is the moon coming between the sun and the Earth, and then the shadow of the moon will hit the Earth, and the shadow of the Earth will hit the moon. And so what we get is a solar eclipse here, but you have to be standing where the shadow hits. And you get a lunar eclipse here. What I want you to notice is that the whole of this side of the planet, the whole of the night side, is going to see that lunar eclipse. Whereas only people standing under the shadow here will see the solar eclipse, and that's important. So I'm just going to digress briefly into lunar eclipses. More people have seen them just because when there is a lunar eclipse, the whole of that side of the planet can see it if the weather is permitting. And I'm not going to focus in any more than that, but it's something that they're not more common on a global scale than solar eclipses, but for a given location on the Earth, you're much more likely to see it. So let's talk about how often we do get eclipses. Now, let me guide you through this image. We've got the sun in the middle. We've got the Earth going around the sun, and we've got the moon going around the Earth. So if we start down here we've got the Earth, the sun is hitting the Earth, that's the day side, that's the night side. When the moon goes around, when it's in this position, it's up here. Its shadow is not hitting the Earth. Likewise, the moon is down below, the Earth is not blocking out the light from the sun. But the Earth is moving in its orbit, and this angle that the moon's eclipse is at, that's going to stay at the same angle. So as we move around the sun, when we get to here, now when the moon gets to new moon, when it's lined up with the sun, it really is lined up and its shadow will hit the Earth. Likewise, in the same month, we're going to have that the Earth is lined up with the moon at full moon, and the full moon will be a lunar eclipse. But the Earth's going to keep moving, so now it's out of alignment again. And when we get round to this side, it is fully out of alignment. And so at this side, we have a full moon and a new moon, and we don't get any eclipses. all the way around this side. The Earth is keeping moving, and when it gets back to here, we can see it's lined up again. So now what we've got is the moon will be in lunar eclipse, and we have the moon lined up with the Earth, and we get a solar eclipse exactly there. So let's just look at this from what's going on. We get a solar eclipse here, but then the moon is not lined up until we get all the way around to here, half an orbit away, and then we get an eclipse again. So we actually get an eclipse approximately every 6 months. There is some sort of solar eclipse on the planet every 6 months, more or less. Now, when we're looking at the eclipse, we would be standing on that one point on Earth that is in the shadow. So here you can see the Earth, you can see the moon, you can see the sun. This little spot here, that is where you need to be standing to not be able to see the sun at all. If you are in this slightly lighter shadow, you're seeing a partial eclipse. So if you stood here, you can see part of the sun, but not all of it. So we have a partial eclipse in this large area and a total eclipse onto this little dark spot. But remember, everything is moving. So the moon is moving in its orbit on this green line. The Earth is moving in its orbit on this blue line, and the Earth is spinning. So the shadow is only going to be at this point for a few moments, and then it's going to have moved to here, and then to here, and then to here. So what you get is an area of the globe that can see the eclipse, that is a stripe across the planet that is drawn out because of these motions. And that stripe is typically less than 100 miles across and maybe a few thousand miles long. So just to show you what those look like, this is a map of all the eclipses for 50 years. That's from 2010 to 2060. And I want you to take away a couple of things from here. First of all, you'll see that in a 50-year period, most of the planet doesn't see a total solar eclipse. You'll also notice that most of the time it's over ocean. This makes sense. Most of the planet is ocean. That means that they're often inaccessible, and they happen to be over inaccessible places. The last one that happened in the US was in 2017. That's this line over here. And the one that we're most interested in right now is this one in 2024 that's going to come over Texas. Now, there are different types of eclipses, and we can have a total eclipse, but we can also have what's called an annular eclipse. And this is because of the orbit of the moon. So let me show you what happens. I'm sure most of you have heard of the supermoon. The supermoon is basically when you have the biggest full moon of the year. But why does the moon change in size? It's not the physical moon that's changing, it's its distance. If you put something towards you, it looks bigger. If you move it away from you, it looks smaller. Same thing happens with the moon. Its orbit is not a circle, it's elliptical, as drawn here. And when it's closest to the Earth, and that's what we call perigee, it's about 10% closer than it is when it's at its furthest point. So because it's closer to us, it is going to be bigger. It's going to be about 10% bigger than it is at its furthest point. And that's really interesting because, you know, it really does look bigger. Now, we don't notice it because we don't see them side by side, but we do get a full moon when the moon is also at perigee, at its closest point, about once a year, and that is the supermoon. How does this relate to eclipses? Well, now we've got together the fact that we've got the sun, we've got the Earth going around the sun, and the moon going around the Earth, and when the Earth is closest to the sun is slightly bigger. The Earth's motion around the sun is also not circular, it is elliptical. But the difference in distance is only about 3 or 4%. So the sun doesn't change in size quite so much. But it's slightly bigger when we're closest, which is actually in January, and slightly smaller when we're furthest, which is around Independence Day. Okay, so you can imagine now that if the sun is, we're at the closest to the sun, so it's its biggest, and the moon is closest, then you actually get a matching up of size. But sometimes you might have the Earth closest to the sun, but the moon at its furthest point. And if that happens, then the moon isn't quite big enough to block out the whole of the sun, and we still see the edge of the sun. And that is an annular eclipse. So what you can see here is, this is showing you how the size of the moon changes. So the moon can actually be bigger than the sun even when we're closest to the sun. So in January, if we have the moon at its closest point, we're going to get to see a solar eclipse. On the other hand, when it's at its smallest, it's actually not going to be big enough to block out the sun even when we're furthest away in July. And so you have to get the right matching up. And what happens is you can still see the edge of the sun. And that's what we call an annular eclipse. A donut, the technical term for that is an annulus. So the term annular is we're seeing that donut shape, the edge of the sun. Okay, so just to kind of bring all of that together, here I've got the sun, here I've got the Earth and the Moon, and if you're standing at point A, you're going to see a total eclipse that looks like this. It's actually going to be darker than that. We'll come back to that. If you're in section B, that's where you can see part of the sun, and you're going to see a partial. Now remember that the spot moves across the ground, so you're always going to see a partial on the way to seeing a total eclipse. We can also get an annular eclipse when the moon isn't quite close enough, and so now when you're standing here, you're going to see that ring around the edge of the sun. Now, I already showed you a map of all the eclipses for 50 years. Now this one shows both annular and total. So the blue lines are total eclipses and the red lines are annular eclipses. And this is for the first 20 years of the 21st century. And so most of these have happened. In fact, the only one that hasn't happened yet is this one here. Again, you'll see that we have eclipses all over the globe, that most of them are on ocean, and a lot of the planet doesn't get to see an eclipse in that 20-year period. You can see here that we had the total eclipse that went all the way across the US in 2017. I was lucky enough to be in Missouri. And then we had this one in 2012, which was an annular. I actually took my kids down to New Mexico, and we saw that one too. So let's look at the next 20 years too. Again, the red lines are the annular eclipses, the blue lines are the total eclipses. The one I want to draw your attention to is this big X drawn here. This is a total eclipse that happens in 2024. This is an annular that happens in 2023, and where it crosses is South Texas. Where we are right now, you are going to get to see this. Okay, so let's talk about what you see during a total eclipse before we focus in on those specific eclipses that are coming to us. So you start with the moon moving in front of the sun, and as it moves in front of the sun, you get a partial eclipse. And you start with a tiny bite out, and as the moon moves further and further in front, you see less and less and less of the sun. During this time, you need to wear special safety glasses. I have some here. And it's not safe to look at the sun until it's completely eclipsed. But during this time, there's all sorts of interesting things to see. First of all, the shadows under trees are really interesting. What happens is, if you look under a tree on a normal day and it has that kind of dappled effect, what you're actually seeing is that all the gaps between the leaves, so you've got leaves overlapping and you've got gaps between them, each of those gaps acts almost like a lens, and it makes a circular image of the sun. And so you get the sun imaged all over the ground, and that's why you don't see nice shapes of leaves on the ground under a tree. But during the eclipse, the sun is no longer a circle, and so you start to see the shape of the sun being eclipsed in the shadows, and that's what you can see in this image under the tree. You also have some interesting effects on animals and plants. Birds will behave differently. They sense that it's getting darker. Now, if you weren't paying attention, you might think you were heading into a thunderstorm or something. The sky changes color, but it's very subtle. And even when you've got most of the sun blocked out, it feels maybe a little twilighty, but it's weird. But the birds really notice, and so do other animals, and they start to behave like, oh, it's close to sunset. We should be, doing our swarming thing that birds do. You also get some other things happening with beasties. Here you can also see, so remember I said about the trees, you can also just make holes in things. So this is actually a sheet of paper. This is from the Annular Eclipse in 2012, and they've used a hole punch to just punch holes and make this. And so the sunlight is passing through here, and for each of these circles we get an image of that partial eclipse. So you can make all sorts of ways to do this. You can also use things, so that's we have a close-up here of that image of the passing through the hole punch. You can use a colander to be able to see those shapes, anything that gives you little holes so that you can pass the light through it. You can even use your hands, hold them up like this with the sun passing through. You may have to move them back and forth and squeeze them together to get the focus right, but then you can see those shapes in the of the sun coming through the gaps in your fingers. So it's a really cool thing that you can do as the sun is getting more and more blocked, but we haven't got to the total eclipse yet. Now, like I said, even when you can see a tiny sliver of the sun, it's still not safe to take those safety glasses off. As you're blocking out more and more of the sun, you start to see what's called Bailey's beads. Bailey's beads are basically where you're seeing the surface of the moon. Remember, the surface of the moon is not smooth. It has craters and mountains. And so what you're seeing here is valleys and mountains, and you're actually seeing that at the edge. And so you see the last bits of sunlight coming through. So let's focus in on that for a few seconds. So here you can see the sun is almost blocked out, and we're seeing just a little bit of it. We're seeing less, and we're starting to see those valleys. We're seeing less and less. This red stuff that's popping up, that's real. It really is red light. and I'll come back to that in a second. But here you can see we've got these bumps and wiggles, and the last bit of the sun that we're seeing is just peeking through. Again, even when there's that little, it's dangerous for your eyes because the sun is so bright. And so the last thing that you see as the sun is getting blocked out, here you can see the moon is almost in the way. There's one valley that's letting in light, and that's called the diamond ring because you've got this bright bit here, but you can start to see the atmosphere of the sun. And so what we're seeing here is, it's called the diamond ring, and it's the last thing that happens before the total eclipse. And then the moon is in the way, and you cannot see the main part of the sun at all. And what pops up is this white glowing stuff. We started to see it during the diamond ring phase, but it's really glowing now. Now that's always there. It's about as bright as a full moon. But because it's so much fainter than the sun, it's 1,000,000 times fainter than the sun. Even with a tiny fraction of the sun showing, it's really hard to see it. I want you to think about, when you're looking into a dark room and it's very bright, you cannot see the details in the room. And that's kind of what's happening here. The glow is always there, but because the sun is so bright, you just can't see it. So let's focus in on this a little bit. This is an image from the 2017 eclipse by Rick Feinberg. And what you can see here is this is really what you get to see. If you were lucky enough to see the 2017 eclipse, this sort of should have been what you see. These red parts here, these are flares and loops and prominences that you see on the surface. If you've ever seen nice images of the sun, they really are red. And that has to do with, it's kind of like a neon light, but instead of being neon, it is hydrogen gas. And that's what's happening there. But you can see the sky is now darkish. You can see stars. This is Regulus in the constellation Leo. Where I was in Columbia, Missouri, we didn't get as dark. This one was taken in Madras, Oregon. But where I was in Columbia, Missouri, it wasn't quite as dark. We could see Jupiter, but we couldn't see any stars. So how dark it gets depends on all sorts of different things in the sky conditions. But what you can see is this dark hole where the sun is completely blocked out by the moon. You can then see the atmosphere of the sun away from the moon. And then as you move away from the sun, it's going to get lighter and lighter because you're getting scattered light that's getting into the atmosphere. So it's dark up near where the sun is, and then it gets lighter and lighter down to the ground. Now, depending on where the sun is, it'll have slightly different effects, but what you get then is, as you get down to the horizon, now what you're seeing is sunset colors all the way around the horizon. So if you imagine what it looks like after sunset and you've got those beautiful reds on the western horizon, well, now those colors go all the way around. So it's useful to be in a place where you've got a good 360-degree view. At the same time, it's going to get a little bit cooler. Remember, we've just blocked out the sun. Think about what it's like when a cloud comes in front of the sun. Well, this is a bigger effect, so the temperature drops. And it also gets a little bit windy. That has to do with the temperature drop and what effect that has on pressure. So you get some breezes coming in. Animals are going to react. Birds tend to stop swarming and go to bed. Bees stop buzzing. Other insects do things. And so you can even see some plants will react. If they're plants that react to following the sun, they may close up their leaves. So there's a whole bunch of things that you're going to experience during the total eclipse. So let me now focus in on the eclipses that are coming to South Texas. We have one in October 2023 and one in April 2024. The one in October 23 is an annular eclipse where you can still see the edge of the sun. Now remember I said that even when you have a tiny fraction of the sun showing, you still can't see, look at it safely, and you can't see the atmosphere, which we call the corona. And so that's what this is showing here. In 2023, we'll still see the edge of the sun, but in 2024, we'll see the whole corona because the sun is completely blocked out. So let's focus in on that 2024 eclipse for now. This is showing the path of the eclipse. So what we've got is the path of the eclipse runs from Mexico all the way to Canada, and it goes over a big swath of Texas. If you're not on the path of totality, you'll still get a partial eclipse. You can see even up here in Oregon, they're getting a 25% eclipse. Likewise down in Miami, they're getting a 45% eclipse. As the eclipse path, as we follow the eclipse path, you're going to have a solar eclipse all the way along here, but we're going to be in a really great position to see it down in South Texas. Now, I want to talk about how long eclipses last, and there's a couple of things we have to talk about. So this is showing you the Earth going around the sun and its elliptical orbit where it's closer to the sun in January. when the Earth is closest to the sun, it's moving faster. When the Earth is furthest from the sun, it's moving slower. You can kind of think of this as if you've got something like a ball on a string and you're swinging it around. If you've got a longer string, it can swing slower and still stay up. If it's a short string, you have to swing it much faster. That's kind of what we're looking at here. As the Earth's getting in, it's actually being accelerated by the gravity of the sun, and it will be getting faster. But then it gets fast enough to start to pull away, but the sun is still pulling on it, so it slows down a bit. So it comes back in. This is normal for anything that orbits anything. So the moon, when it orbits the Earth, that is moving fastest when it's closest at perigee and slowest at apogee, its furthest point. So depending on where we are in our orbit, where the moon is in its orbit, there will be different speeds of motion, and depending on your latitude, that will also affect the speed at which the ground is moving. And so if you put all those together, eclipses can last from, well, if you're on the edge of an eclipse path, a few seconds to up to about 6 or 7 minutes. And so we get different durations. So if we look at our eclipse, here we are, we can see, this shows you the center line, and I'm going to come back to that. This is where UBarU is, the star is. And so we're right in the middle of the path, or very close to the middle. Being close to the middle is a good thing. So you can imagine the sun's shadow is a circle. It's actually more of an ellipse, but a circle is close enough. As that circle moves along, if you are at point 1, you are not going to be under that shadow for as long as if you were at point 2. The closer to the edge of the path you get, the less time you get in the eclipse. So it matters where the Earth is in its orbit, where the moon is in its orbit, and where you are on the eclipse path and your latitude. And all of those things put together dictate how long you get in eclipse. So now this is showing you, this has got actually contours. I don't know if you can see the details here, so I'm going to read them out. These contours actually show where the longest duration is. So the longest duration is about 4.5 minutes, and it's down here in Mexico. But if we come up to where we are right now, here's San Antonio, we're right around here, we're between the 4:10 and 4:20. So the total eclipse up here is going to be over 4 minutes. Down in San Antonio, if you're actually in downtown, you won't see it. If you're up near where UTSA is, you're still going to get about 2 minutes because the time goes up fast as you get closer into the center. So now focusing in on where we're going to be, here you can see that path again. The blue line is the center line. If you're not in the darkened part, you're not going to see a total eclipse. Now remember, I said that even with a tiny fraction of the sun showing, you don't get to see all the stuff. You don't get to see the corona. It doesn't get dark. Remember that even if 1,000th, 0.1% of the sun is showing, it's still 1,000 times brighter than the full moon, and so it's just really bright. And so you have to be in the shadowed area in order to see the total eclipse. If we focus in on where UBarU is, this actually gives you the times. I'm guessing you can't see this, so I've made a bigger version. This is actually from this website here. It's using Google Maps, but it tells you all of the details of the eclipse. So for the location of UBarU, we have the eclipse starting at, and this is 1832, but this is UT, which is basically the same as GMT. So for Texas, it should be 1 p.m. because we'll already be in summertime, daylight savings time. So it'll be 1:32 that the eclipse starts and 1:36 when it ends, and the middle of the eclipse will be at 1:34 p.m. This also tells you how high in the sky it's going to be, so how high up do you have to look, and also the azimuth, so this is basically the direction that you need to look in to find it. So this is a really useful map system for figuring out where you want to be in the eclipse. Now, this was the total eclipse that I was talking about, and that eclipse is going to happen in 1333 days. The annular eclipse is going to happen sooner. That happens 6 months earlier. That's the time before that you get the matching up of the new moon and the full moon. And so let's focus in on that one for a second. So here I've got a map of the annular eclipse. This is a photo of an annular eclipse, so just to remind you, you can still see the edge of the sun. So the special eclipse glasses are really important. And again, you get to see a partial on the way, and the whole of the US gets to see a partial. So let's say you're up where I used to live in Missouri, you're going to get to see a 60% partial eclipse. But where we are, we're going to get to see a complete annular eclipse. And so here I've got the path of the annular. Again, the closer to the center line, the more time you get in annularity, so with the sun and moon directly lined up. And you can see here for UBarU, it's about halfway across. You can also see on here, this one has those contours with the times on. So for where we are right for UBarU, it's going to be again somewhere in the 3 to 4 minute range that it'll actually be an annular eclipse. Again, I've used that same mapping website, and so for the annular eclipse at UBarU, what we're going to see is the annular eclipse will start at, and this is in October, but I think it's before we switch back to non-daylight savings, back to standard time. So it's going to be at 11:50-ish, and you get about 4 minutes in the annular eclipse at UBarU. But again, you can use this to find it, and again, the website is over here. Oh, sorry, and I zoomed in to show you it a little more closely. So you can see here the obscuration is just under 90%. So there's still 10% of the sun showing, and that means that it's 100,000 times brighter than the full moon. It's really not safe to look at without protection, and it doesn't get super dark. So let's talk about that protection. You can get glasses like this. For the eclipse in 2017, these were distributed in various ways. You can see this one has Roadrunners on it. They are really important. There are other things that you can do too, but that's a really important thing. And I can help you connect with the suppliers. You can get them personalized. You can get them made for your business, and so on. What you see through these glasses, so here you can see a nice picture of my eclipse glasses. What you see through these glasses looks like this. So you're looking through, and everything else will be dark, and all you can see is the sun. Remember, the sun is so bright that we only want to see about 1/1000th of it. And so this film that is in the glasses is so opaque. If you can see anything other than the sun, they are not protecting you. So you really want to be careful about making sure they are fully protective. And I'm just going to finish up by pointing out this website. This is eclipse.aas.org. This is a website that was put together for the 2017 eclipse. It's now being revamped for the 2024 eclipse. It was built by the American Astronomical Society, which is our professional body as astronomers in the US, and the National Science Foundation. And we will continue to be working on this stuff. And so I'm going to stop there, and I hope that this has been informative, and I will look forward to seeing you at the eclipse. Bye-bye.